So again, looking at this example, we wanted to know when is a function increasing or decreasing, which to us in calculus means when is the derivative positive and when is it negative. Again, we're using the sign chart method. So the first step is to find those critical values. To do that, you find the derivative of the function. The derivative of this function, using the power rule and chain rule, bring the power down would be 2/3 x squared minus 4 to the power minus 1, and then don't forget to multiply times the derivative of the inside. That's all written out right here. And then you simplify it because it has a negative exponent, throw it into the denominator. You have the 2 times the 2x, which gives us the 4x. Simplifying, we have 4x over 3 times the cube root of x squared minus 4. That's our derivative of our function. Remember, for critical values, we have two questions. When is it equal to 0? And when is it undefined? So, when a fraction is equal to 0 is when the numerator is equal to 0. 4x equal to 0 gives us x equals 0. Notice, if I plug 0 into the original function, the function is defined, so that is an actual critical value. A derivative is undefined when its denominator is equal to 0. So if you set the denominator equal to 0, divide both sides by 3, cube both sides, you end up with x squared minus 4 equals 0. Factoring, setting it equal to 0, we get positive and negative 2. Notice if we put plus and minus 2 into the original function, both of those are defined as well. So all three of these values, 0, negative 2, and 2, are critical values. We then move on to the next step, which is to create the number line, plotting the points negative 2, 0, and 2. We determine the intervals, the first interval being negative infinity to negative 2, negative 2 to 0, 0 to 2, and 2 to infinity. Remember, when x equals 0, my derivative was 0, and when x equaled negative 2 and 2, my derivative was undefined at those points. So the next step to do is to test a number in each one of those intervals using the sign chart. Remember, you're going to pick an x value in each one of those intervals and plug it into the derivative of the function. Again, we don't care what the actual number is, just whether it is positive or negative. So in the first interval, negative infinity to negative 2, I chose the number negative 3. Plugging negative 3 in the numerator, I got a negative number. Plugging negative 3 in the denominator, I got a positive number. And a negative divided by a positive is a negative. Plugging negative 1 into the numerator, I got a negative number. Plugging negative 1 into the denominator, I also got a negative number. A negative divided by a negative is positive. Plugging 1 into the numerator, I got a positive number. Plugging 1 into the denominator, I got a negative number. A positive divided by a negative is a negative. Plugging 3 into the numerator, I got a positive. Plugging 3 into the denominator, I got a positive. A positive divided by a positive is a positive. Now, step 4 is interpret the answer. Because it was negative in the first test point, it has to be negative on that entire interval. Once a derivative is negative, we know our function is decreasing. When it was positive on the second test point, it has to be positive on that second interval. A positive derivative means my function is increasing. My third test point was negative, which means that entire third interval is negative. Again, if the derivative is negative, my original function is decreasing. My fourth test point was positive, so that entire interval is positive. Because the derivative is positive, my function is increasing. That allows me to go through and look at the total intervals of increasing was the intervals negative 2 to 0 and also 2 to infinity. You could put the little union sign right there if you want, but it's not required in my course. Decreasing, if I wanted to know the intervals of decreasing, I look at negative infinity to negative 2. And also it was decreasing at 0 to 2. Again, you could put the union there if you want, but it is not necessary in my course. Let's work through this next problem together. Again, we want to know when is it increasing, when is it decreasing, which means we need to look at the derivative. When is the derivative positive and negative? That means we need to use the sign chart method. First thing I need to do is find that derivative and find those critical values. This is a quotient, so I'm going to use the quotient rule. It's the bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom squared. And now I'm going to do some simplification. Simplifying the numerator, don't forget to distribute that negative to both terms. I had 2x squared minus x squared minus 1. Combining like terms and simplifying further, let's see what we get. So I have the derivative of my function is x squared minus 1 all over x squared. Again, to find those critical values, I need to consider two cases. When is the derivative equal to 0, and when is the derivative of the function undefined? Anytime we have a fraction, the derivative is equal to 0 when the top is equal to 0. Anytime it's undefined is when the denominator, or the bottom, is equal to 0. Let's solve both of these and see what we get. So on the first one, if you don't forget negatives and positives, I'm getting -1 and +1. And for when it was undefined, I'm getting x equals 0. I want to know, are these truly critical values, or are they just points where we have to break up the derivative? To check that, I need to consider those values plugged into the original function. Consider -1 and 1 plugged into this function right here. The only time we're really concerned with a fraction is, would my denominator be 0, because then my function would be undefined. -1 and 1 could both be plugged into the denominator. That wouldn't cause us a problem. However, when we look at x equals 0, if we plug that into the original function, the denominator would be 0, meaning that that point is undefined. So x equals 0 is an x value that we care about and need to break it up, but it is not a critical value because it is not in the domain of the original function. However, -1 and 1 are critical values. Right now, this might not seem important, but in the next section, this will be a very important thing to note. So let's continue on with our process. Next thing we need to do is look at the number line. We create the number line, and we plot our critical values in any points we need to break it up, which was at -1, 0, and 1. The derivative at -1 and 1 was 0, and the derivative when x equals 0 was undefined. Let's break it up into our intervals. The first interval would be -infinity to -1. The second interval, -1 to 0. We have 0 to 1, and then 1 to infinity. We need to consider a test point in each one of these intervals. The way that we do this is the next step, which is using the sign chart. We're going to use the derivative is what we're plugging it into. I'm going to go ahead and plug it into the factored form of the derivative, because that helps me determine the sign at a faster rate. And I'm going to choose a point in each one of those 4 intervals to plug it into the factored form of the derivative. In the first one, I'll choose the point -10. And the second one, I actually need to pick, how about something like -1/2. The third interval, I'll pick something like 1/2. And the last interval, 10. Again, these are completely random numbers that I picked. They just have to be in those intervals. I'm going to go ahead and test the sign of each one of those factors for those intervals. If I plug in -10, -10 into the numerator, I'm plugging -10 into the numerator and the denominator of the derivative. If I plug in -10, -10 plus 1 is negative, -10 minus 1 is negative, and -10 squared is positive. A negative times a negative over a positive all over is positive. Because it's positive in that interval, I know that it has to be positive in the entire interval. Go on to -1/2. Looking at my factors, -1/2 plus 1 is positive, -1/2 minus 1 is negative, -1/2 squared is positive, so this is going to be a positive times a negative over a positive, which is negative. Because it was negative at that test point, it has to be negative at every point. I plug in 1/2. 1/2 plus 1 is positive. 1/2 minus 1 is negative. And 1/2 squared is positive. A positive times a negative over a positive is negative. Again, since it was negative at that test point, it has to be negative at every test point, or every point in that interval. I look at the number 10. I'd have a positive. I'd have a positive. I'd have a positive. All positives would give me positive, so it's positive at every point in that interval. So now I just need to sit back and interpret all that work that I've done. Again, my function, anywhere the derivative is positive, is increasing. Anywhere the derivative is negative, is decreasing. It's very important to note that I have to break it up at the points. I can't say it's a continuous interval in between those points. So for instance, where is my function increasing? I'm looking for increasing here. It was increasing on the intervals -infinity to -1, and it was increasing on the intervals 1 to infinity. When I'm looking at where is my function decreasing, For decreasing, I had it was decreasing from -1 to 0, and it was also decreasing from 0 to 1. It might be tempting to try to write that it is decreasing from -1 to 1 because those two intervals are right next to each other, but you cannot do that because the function is not defined when x equals 0. So we have to break it up. We have to say it was decreasing from -1 to 0 and 0 to infinity. Again, notice in all of these we are using parentheses.